On this worksheet, we're going to go through an example of determining the rate law and also determining the rate constant for this reaction right here, given this set of data. So as a reminder, when you're asked to determine the rate law, you're really just being asked to solve the exponents in this generic equation. Rate equals little k, a to the x, b to the y. In this equation, the little k is the rate constant, and we will be solving for the rate constant in this problem. The concentrations in brackets here are always going to be the concentration of the reactants, never the concentration of the products. And these exponents, x and y, these are the numbers that we're solving for or we're calculating when we're solving for the rate law. These numbers don't have anything to do with stoichiometric coefficients, even though sometimes they do coincide with them. To solve this problem, we're going to be using 3 sets of data. I'm going to number them 1, 2, 3. And to begin, we're going to select 2 sets of data. We're going to start by focusing on reactant number A. So we're going to select 2 sets of data where the concentration of A is identical. That would be data set 1 and data set 2. The concentration of A is exactly the same. We also want to make sure for these 2 sets of data that we're selecting, while the concentration of A is identical, the concentration of B needs to be different. And that does work for data set number 1 and number 2. Again, we want, for these 2 data sets, we want the concentration of one substance to be identical and the concentration of the second substance to be different. What we're going to do is I'll just start with data set number 1. We're going to take data set number 1 and we're going to plug in all of this information right here into the rate law. So I'm just going to kind of make a 1 because this is going to be for data set number 1. Starting with the rate is 0.320. I'm going to leave units off. And that is equal to the rate constant. We don't know what that is yet, so we're going to continue to use K. We want, for data set number 1, the concentration of A, which is 1.5. And we're going to be raising that to the X. We don't know what X is. And then also for data set number 1, the concentration of B is 1.5, and we'll be raising that to the Y. Now we want to do the exact same thing for data set number 2. Remember I said we want to pick 2 data sets where the concentration of A is exactly the same, the concentration of B is different. So for data set number 2, now we're going to do the same thing. We're going to take all of this information and we are going to plug it into the rate law. For data set number 2, the rate is also 0.320. We still don't know the value of K. For data set number 2, the value of A is 1.5, and we're going to raise that to the X. And for data set number 2, the value of B is 2.5, and we'll be raising that to the Y. And what we're going to do is turn this into a couple of fractions. So we're just going to kind of make it a fraction like this. Only specifically, I want to make 2 fractions, the left side and the right side. Also, what I'm going to do is take that equal sign and I'm going to put it in the middle so it just looks like a normal math problem. Then we're going to take this math problem and we're going to simplify it as much as possible. For example, we don't know what K is, but we know that K is the same thing as K. So K divided by K is going to cancel itself out. We'll cross that off. Also, we don't know what X is, but we do know that 1.5 to the X is going to be equal to 1.5 to the X, so we can cross that off as well. And then, of course, as you know, 0.32 divided by 0.32 is mathematically just going to equal 1. So we can simplify this equation quite a bit. 0.32 divided by 0.32 is 1, and that is equal to 1.5 over 2.5 raised to the Y. Since both of these are raised to the Y, I can put the 1.5 and the 2.5 in its own set of parentheses and the Y on the outside. And all we have to do now is solve for Y. Now you might be able to figure this out just by looking at it. Depending on how familiar you are with exponents, you might say this is only going to work if Y is equal to 0. But let's pretend like maybe you're not that comfortable with exponents and we need to actually work the math out on this the long way. So I'm going to begin by going 1.5 divided by 2.5, and that gives me 0.6. And that's raised to the Y. In order to solve for this exponent, you're going to use either log or natural log, your choice, and you're going to take the log of both sides. The log of 1 is equal to Y times the log of 0.6. The log of 1 is 0, and the log of 0.6 is negative 0.2. And then we're just going to solve for Y, and again, we get Y equals 0. That's one of our exponents solved. We've got a little bit of this rate figured out. I'm going to copy this down here. Rate equals K, A to the, we still don't know what, I'm going to leave space for that, B to the 0. Let's go ahead and repeat this process so that we can figure out the value of x. And what I'm going to do is just kind of move this down and out of the way. To solve for the value of x, we're going to do, like I said, the same thing. We want to pick two sets of data from all of these sets of data. This time we want, so in the first time we wanted two sets of data where A was exactly the same. Now we want to find two sets of data where B is exactly the same. And that's going to be data set number 1 and data set number 3. And just to kind of make this a little bit easier to look at, I'm just going to temporarily cross off data set number 2. So we're going to write two rate laws again, this time using data set number 1 and data set number 3. We're going to fill in as much of this information as we can into the rate law up here. For data set number 1, the rate is 0.320. That's equal to K. The concentration of A is 1.5 to the X. The concentration of B is 1.5 to the Y. And we're going to divide that by all of our data for data set number 3. For data set number 3, the rate is 0.64. That's equal to K. The concentration of A is 3.0. And the concentration of B is 1.5. We're going to cross off what we can. The value of the rate constant is the same. 1.5 to the y is the same as 1.5 to the y. And we'll simplify this. 0.32 divided by 0.64 is 0.5. And that is going to be equal to 1.5 divided by 3 to the x. Now we'll simplify inside those parentheses. 0.5 is equal to 0.5 to the x. And again, this one you can almost certainly do in your head. X is 1. Now to determine the value of the rate constant, what we're going to do is go back to our data one more time. We're going to pick any data set we want. Literally, it could be any data set that you want. I'll go ahead and I'll just pick data set number 1 because it's on top. We're going to plug all of these numbers back into the rate law that we have figured out, and we are actually just going to solve for K. So for data set number 1, our rate is 0.320, and this is where we do want to pay attention to units, meters per second. The value of K is what we're trying to figure out. For A, we have 1.50, and that's unit of molarity, and that's raised to the 1. And for B, we have 1.50 units of molarities, and that's raised to the 0. So we get 0.320 molarity per second. That's equal to K times 1.50. And remember, anything raised to the 0 is just 1. So this will just be equal to 1, and we can get rid of those units. To solve for K, we're going to go 0.320 molarity per second, and that's going to be divided by the 1.5 molarity. Those molarity units are going to cancel, so our K is going to end up having units of 1 over second. 0.32 divided by 1.5 is 0.213, 1 over seconds, or another way that we could write that is 0.213 seconds to the minus 1.